In computer science, function composition is an act or mechanism to combine simple functions to build more complicated ones. Like the usual composition of functions in mathematics, the result of each function is passed as the argument of the next, and the result of the last one is the result of the whole. Programmers frequently apply functions to results of other functions, and almost all programming languages allow it. In some cases, the composition of functions is interesting as a function in its own right, to be used later. Such a function can always be defined, but languages with first-class functions make it easier. The ability to easily compose functions encourages factoring functions for maintainability and code reuse. More generally, big systems might be built by composing whole programs. Narrowly speaking, function composition applies to functions that operate on a finite amount of data, each step sequentially processing it before handing it to the next. Functions that operate on potentially infinite data are known as filters, and are instead connected in a pipeline, which is analogous to function composition and can execute concurrently, composing function calls. For example, suppose we have two functions and, as in. Composing them means we first compute, and then use to compute. Here is the example in the C language. Float x, y, z, y equals g, z equals f. The steps can be combined if we don't give a name to the intermediate result. Z equals f. Despite differences in length, these two implementations compute the same result. The second implementation requires only one line of code and is colloquially referred to as a highly composed form. Readability and hence maintainability is one advantage of highly composed forms, since they require fewer lines of code, minimizing a program's surface area. DeMarco and Lister empirically verify an inverse relationship between surface area and maintainability. On the other hand, it may be possible to overuse highly composed forms. A nesting of too many functions may have the opposite effect, making the code less maintainable. In a stack-based language, functional composition is even more natural. It is performed by concatenation, and is usually the primary method of program design. The above example in fourth GF, which will take whatever was on the stack before, apply G, then F, and leave the result on the stack. See postfix composition notation for the corresponding mathematical notation, naming the composition of functions. Now suppose that the combination of calling f is frequently useful and we want to name foo, return f. Example in fourth. FooGF. In languages such as C, the only way to create a new function is to define it in the program source, which means that functions can't be composed at runtime. First-class composition. In functional programming languages, function composition can be naturally expressed as a higher-order function or operator. In Haskell, the example given above becomes foo equals f, g using the built-in composition operator, which can be read as f after g or g composed with f. The composition operator itself can be defined in Haskell using a lambda expression. To cf, g equals x to f. The first line describes the type of it takes a pair of functions and returns a function. Note that Haskell doesn't require specification of the exact input and output types of f and g, only the relations between them. This makes a polymorphic operator. Variants of Lisp, especially Scheme. The interchangeability of code and data together with the treatment of functions lend themselves extremely well for a recursive definition of a variadic compositional operator. X, if no argument is given, evaluates to the identity function x. Examples greater than set. Anonymous composition 5 greater than 0 plus 5 Perl 6. Like Haskell has a built-in function composition operator. The main difference is it is spelled as o. My and foo equals an f and g. Also like Haskell you could define the operator yourself. In fact the following is the Perl 6 code used to define it in the Rakudo implementation. The implementation has a slightly different line here because it sheets proto-sub-infix less than greater than is equivalent is association less than left greater than asterisk multi-sub-infix less than greater than, and f allows at array to work when at array has one element multi-sub-infix less than greater than count greater than 1. 2 args f g args 2 args fg args alias it to the Texas spelling my an infix less than o greater than equals an infix less than greater than. In other programming languages you can write your own mechanisms to perform function composition. In Python, a way to define the composition for any group of functions is using reduce function. Def compose. Compose a group of functions into a single composite func. Return reduce funcs. Example f equals lambda x plus 1 gram equals lambda x asterisk 2h equals lambda x3 call the function x equals 10 asterisk 2 plus 1 equals 15 print. In JavaScript we can define it as a function which takes two functions f and g and produces a function. Function O, return function, return F. Languages like Ruby let you construct a binary operator yourself. Class procdef compose to other underscore fn dot call end alias underscore method plus compose end f equals to x asterisk 2 g equals to x asterisk 3 call equals greater than 13,824 research survey. Notions of composition, including the principle of compositionality and composability, is so ubiquitous that numerous strands of research have separately evolved. The following is a sampling of the kind of research in which the notion of composition is central. Steele directly applied function composition to the assemblage of building blocks known as monads in the Haskell programming language. May addressed the software reuse problem in terms of composability. Obadi and Lamport formally defined a proof rule for functional composition that assures the program's safety and liveness. Cracked identified a strengthened form of compositionality by placing it into a semiotic system and applying it to the problem of structural ambiguity frequently encountered in computational linguistics. Van Gelder and Port examined the role of compositionality in analog aspects of natural language processing. According to a review by Gibbons, formal treatment of composition underlies validation of component assembly in visual programming languages like IBM's Visual Age for the Java language. Large-scale composition. Whole programs or systems can be treated as functions, which can be readily composed if their inputs and outputs are well-defined pipelines allowing easy composition of filters were so successful that it become a design pattern of operating systems. Imperative procedures with side effects violate preferential transparency and therefore are not cleanly composable. However, if you consider the state of the world before and after running the code as its input and output, you get a clean function. Composition of such functions corresponds to running the procedures one after the other. The monads formalism uses this idea to incorporate side effects and I/O into functional languages.